Hello, in this video for today I'll talk about the central forces. Now, what is a central force? Now, a force field F will be said to be central if it is always directed towards the origin, and if the magnitude of this force depends only on the distance r from the origin. So we think of the coordinate system. We think of a coordinate axis such as the xy plane, and we think of a force that is directed towards the origin O here, and whose magnitude depends on the distance r from the origin. Now, such a force, we call it central. In this case, we say that the magnitude of F is a function of r, and the direction is towards the origin. So that in this case, we write F, because we can think of a vector, a position vector which is in this direction, and call it vector r, then the force F will be in the opposite direction of r. So that if the direction vector is defined as r hat, which is the position vector r divided by its magnitude, then we write F here is equals to, remember, any vector can be expressed as a product of its magnitude and direction. So when we write the force F, we can write it as the product of the magnitude of F times the direction of the force F. So in this case, because the direction is opposite that of r, we put the negative here to indicate that the direction is opposite. But remember, F, the magnitude of F is equals to Fr, so we come up with this kind of an expression for the central force F. So a force field F will be said to be central if it is always directed towards the origin, and two, that its magnitude depends only on the distance r from the origin. So that we write the magnitude of F is equals to a function of r, where r is the distance of the force F from the origin. Oh, now some properties of central forces. One is that a central force is a conservative. And what do I mean by a conservative force? Remember, a force field is said to be conservative if we can find a scalar function, which sometimes we call phi, or sometimes we may call it v. We may denote it by v. V, a scalar function, such that f is the negative gradient of v, or phi. So if we can find a scalar function such as v in such a way that when we differentiate v, when we work out the vector gradient of v and we multiply by -1, we get the force field F. Then we shall say that F is a conservative force field. So for a central force will always be conservative. So that means that we can find the potential function V such that F is the negative gradient of V. And V can be obtained as an integral of F with respect to R. Now, number two is that the angular momentum of a particle moving in a central force field is always a constant. And the other property is that a particle moving in a central force field will move in such a way that its position vector or radius vector drawn from the origin to the particle sweeps out equal areas in equal time. I want us to go through an example here. I try to prove that the path of a particle moving in a central force field is a plane curve. Now, suppose that we consider a force field F, and suppose that this force field is conservative, which means that, it's a central force, which means that the force is directed towards the origin, and the magnitude depends only on the distance r from the origin, so that we can write F is equals to minus Fr times r hat, where r hat is the position, the direction vector. Now, if we work out r cross F, we work out r cross F, and remember that F is equals to minus Fr times r vector, where the unit vector r hat can be expressed as the vector r divided by the magnitude of r. Now we have that F therefore can be expressed as minus Fr divided by the magnitude of the vector r times the vector r. So that if we work out now the dot product of the vector r, not the dot product but the cross product, r cross F, we get minus Fr, remember Fr is a scalar, divided by the magnitude of r, which is also a scalar. Then we shall have r cross r, because of this r here, and now this one, so r cross r. But how do we find r cross r? Remember, from from vector analysis, you have that if you have two vectors a and b, and then you work out a cross b, then you get the magnitude of a times the magnitude of b times sine of the angle between the vectors a and b times the direction vector, where we are thinking of a vector a, that direction, then another vector b in that direction, so that the angle between them here is theta. So when we consider if we consider now, if a is equals to r and b is also equals to r, that is, we consider a special case where a and b are the same, then these are two parallel vectors, so that theta will be 0. Also, think of r and r, these are two parallel vectors, and so theta will be 0. So if we substitute theta is 0 in the expression here, if we substitute theta is equals to 0 in that expression, we'll be looking for sine of 0, which is 0. So that in this case, r cross r is a 0 vector, is 0. So we want to substitute that one here, r cross r is 0, and when we do, everything on the right hand side becomes 0, so that we get r cross f is 0. R cross f is 0. And now, so we end up with the expression r cross f is equals to 0. But we know that f can be obtained as mass times the acceleration, which is the second Newton's law of motion, or we can write mass times the time rate of change of the velocity. because the acceleration is defined as time rate of change of the velocity. In this case, we can write f as m dv dt. We want to substitute this quantity here. We want to substitute this quantity in this equation here, so that we have r cross m dv dt. So when this one is substituted, you see now we substitute, we have that r cross f is 0, and then we have determined that f is given by m dv dt, so we substitute. So we get r cross m dv dt is equals to 0. Now, from the theory of vectors, vector differentiation, we can work out the vector derivative. I want to work it out somewhere. I filled every step here, every space. But if you look at the results here, we want to work out the derivative of m d by dt r cross v, where v is the velocity and r is the position vector. Now, by applying the product rule of differentiation, if we work out this, remember the product rule, so we differentiate r, we first hold r and then differentiate v with respect to t, as we have here. Then we hold now v and differentiate r with respect to t. But it will be important to note that this quantity, dr by dt, is equals to v. Is equals to v, so that when we substitute here, we shall get m, then v cross v. And because this will be parallel vectors, then the product, that quantity will be 0. This quantity here, when we write v cross v, we get 0. This quantity is 0. So that we see that this quantity here will be equals to this one, or we write r cross m dv dt, so that we end up with this expression that we had here. But we know, we had seen from equation, this equation which we call 6 here, that r cross dv dt is equals to 0. So now we want to replace r cross m dv dt with m d by dt r cross v, so that we get that quantity is 0. We get that quantity is 0. So we shall be getting something like this quantity here is what we shall be equating to 0. M d by dt r cross v is equals to 0, or even we can just write r cross v, sorry, that's not exactly true, d by dt of r cross v is equals to 0, because m is a constant and we can divide both sides by m. So if we now integrate both sides of this expression with respect to t, we see that the left hand side will reduce to r cross v, and then the right hand side we have the integral of 0, which will give us a constant, and this will mean that r cross v is a constant vector. R cross v is a constant vector. Now, if we dot both sides of this expression here, this equation 7 now, with R, that is, we have R cross V is equals to a constant. We dot this side with R. We dot this side with R. Then we get the left-hand side becomes the triple product, which is 0. Because now we are getting that R cross V is a vector which is perpendicular to R. If you get this vector and call it A, this vector will be perpendicular to R, to this other vector here. And remember now when we write R dot A, this is the magnitude of R times the magnitude of A times cosine of theta, the angle between them. And because A is a vector which is perpendicular to R, so theta is 90 degrees and cosine of 90 is 0. So this quantity becomes 0. So that means that the constant vector here is equals to 0. This side becomes 0, and so R dot C becomes 0, and therefore R is perpendicular to a constant vector. We conclude that R is perpendicular to a constant vector, and therefore this will mean that the motion of a particle takes place in a plane. Now, for simplicity, we shall assume that this plane is the xy plane, and therefore the origin is at the center of the force. Now, we have example 2. We want to prove that the angular momentum of a particle moving in a central force field is a constant. And we shall start from equation 7 here, this equation. So this says that R cross V is a constant vector. And then we multiply both sides of this equation by M. So when we multiply, we get, we have R cross V is equals to a constant. We multiply this side by M. We multiply this side by M. We can open the brackets here and write MR cross V is equals to MC. And we can also write R cross MV is equals to MC. Remember, C is a constant vector and M is a scalar. So MC will still be a constant vector. So in this case, this quantity here is the angular momentum. And so this means that the angular momentum of a particle moving in a central force field is a constant. The angular momentum of a particle moving in a central force field is a constant. Now, let's look at the equations of motion for a particle moving in a central force field. I'll skip some of the derivations, and then we shall go to the main equations, and then we shall see how to apply the equations to obtain the law of force. Now, the motion of a particle moving in a central force will always remain the plane defined by its initial position and vector, as we have seen in example 1 in the previous section. Now, because the position vector R, the velocity V, and the force field all lie in the same plane, then there cannot be an acceleration perpendicular to this plane. And for simplicity, we shall choose this plane to be the xy plane. So we think of the xy plane, then the position vector R is described by this line. We can think of a force which is located at P, then it will be directed towards the origin. The angle theta is the angle between the position vector R and the positive x-axis, so that we can describe this by a triangle of this form. This side has the length of magnitude r, and so we write cosine of, if this side is x, this side is y, then we shall write cosine of theta is equals to x all over the magnitude of r, and this would imply that x is equals to the magnitude of r times cosine of theta. If you cross multiply from here, if you cross multiply, you get x. And similarly for y, we can write sine theta is equals to y divided by the magnitude of r. We can write sine theta is equals to y divided by the magnitude of r. And from this, we can get y is equals to the magnitude of r times sine of theta. So this side is described by magnitude of r times sine of theta, or the x-axis by the magnitude of r times the cosine of theta. So when we write p here with the coordinate x, y, we can replace x and y with these quantities. We can replace x and y with those quantities. And so when we say the position vector has the coordinate x, y at any instant, then we can write the position vector r has the coordinates, the magnitude of r cos theta, which is x, and the magnitude of r sin theta, which is y, by replacing x and y. Normally we put the equals here, so we get r. We can factor out r here, and for simplicity we shall use r to represent the magnitude of the vector r. So in this case, if we differentiate, if we want to find the time derivative of r, that's the total derivative, see that r is a function of two variables here. It's a function of r and theta. So if we want to find the total derivative dr, then we write the partial derivative of r with respect to r dr plus the partial derivative of r with respect to theta times d theta. So if we want to find the time derivative, then it means that we divide this side by dt, and we divide here by dt, and we divide here by dt. So now the partial derivatives of r with respect to r, because we have the expression for r here, we can differentiate that partially with respect to r, and we can also differentiate partially with respect to theta. So that differentiating partially with respect to r will give us cos theta sin theta, which is this expression here. And differentiating partially with respect to theta will be differentiating cosine of theta to get negative sin theta, and sine of theta to get cosine of theta. Then we have times this r, so that we get this expression here. And these are the position vector in the radial and azimuthal directions. Now we can similarly find the acceleration of the particle by differentiating the expression that we get here again. This is the velocity, and the acceleration is the time rate of change of the velocity. So we can work out that derivative. Now I'll skip the derivation, and then we go to the equations of motion. Once we work out all this, we should get 3 equations of motion. These are the important equations here, the equations of motion. The most important equation will be equation number 9 here, equation number 9, which we write as m h squared u squared d squared u by d theta square minus, plus u is equals to f of 1 over u. In this case, in this expression, h is a constant, m is a constant, and u, this one is supposed to be u, like that. So u is equals to 1 over r, where r is the distance of the particle from the origin. So that when we write 1 over u, that will just be r. So this equation gives the force acting on a particle moving in a central force field. Let's do an example. We have a particle moving in a central force field located at the origin, r is equals to 0, and we are told that this particle describes a spiral. A spiral is something like you start from the origin and it starts moving in that direction, following such a path. So this describes a spiral. R is equals to e raised to power negative theta, and we want to prove that the magnitude of the force is inversely proportional to r cubed. So we write from that equation Fr is equals to mh squared u squared, then you have d squared u by d theta squared plus u. This is the equation of motion. Now u is equals to 1 over r, which is 1 over e raised to power negative theta, because r is given here as the equation of the path. There is e raised to power negative theta, so this becomes e raised to power theta. We can now differentiate u with respect to theta, and we get e raised to power theta, and we differentiate again d squared u by d theta squared, we get e raised to power theta, which is u. Basically this is u, e raised to power theta is u. Now we then substitute this one back here. We are only replacing d squared u by d theta squared, and we shall replace by u. So that when we do that, we get Fr is equals to mh squared u squared, then in brackets we have u plus u. So as we have here, so see that this will be mh squared u squared, then times 2u, and when we open the brackets, we multiply out, we get this expression there, where u is 1 over r, so that we can write Fr is equals to 2 mh squared times 1 over r cubed. Now, because this one is a constant, m is a constant, h is a constant, then we can say that Fr is proportional to 1 over r cubed, or Fr, the force, is inversely proportional to r cubed. We have another example, and probably you can go through this example. It is similar to the question in the next page, written as example 3, which are not done. I will do this one. It is similar to the other one. You are told that under the influence of a central force at the origin, a particle moves in a circular motion which passes through the origin with center at point x is equals to a. and the problem is to find the row of force. So we think of a particle that moves along a circle with center at x is equals to a, and the path moves I want to try and draw as nearly as possible. This is the point here is 2a. So the equation of a circle of this kind is r is equals to 2a cosine of theta. So you see that when theta is 0, that is along the x-axis, r is equals to 2a. It will be at this point. And when you move to 180 degrees, and theta is 180, cosine of 180, by the time you reach 90, theta is 90, cosine of 90 will be 0, cosine of 90 degrees is 0, and r will be 0. So you have moved from here all the way up to the origin here, and then you complete the other half, the other part of the circle. Now, you can refer to your notes on analytical geometry about the circle, the graphs of polar curves, polar graphs to that. Now, the equation is basically of this kind. So when we write u, which is equals to 1 over r, this will be 1 over 2a times the secant of theta. So when we differentiate du by d theta, we get 1 over 2a sec theta tan theta, the derivative of secant of theta. And when we differentiate the second time, d squared u by d theta squared, we'll get 1 over 2a. 2a is a constant. So we differentiate sec theta tan theta, this being a product. Then we apply the product rule of differentiation. So the product rule says that we hold one function, we differentiate the other first. So we can hold sec theta and differentiate tan theta. Then now we hold tan theta and differentiate with respect to theta. We differentiate sec theta. The derivative of tan theta is sec squared theta. So we get sec theta times sec squared theta plus tan theta. The derivative of sec theta is sec theta tan theta. Then we can simplify this. We get 1 over 2a sec cubed theta plus tan squared theta times, if we are opening the brackets here, tan theta times sec theta tan theta is tan squared theta times secant of theta. Now, from trigonometry, we can write 1 over 2a. Remember, the first term just remain that. But the second term, tan of theta, tan squared theta, can be expressed as sec squared theta minus 1. So then we multiply this by secant of theta, so that when we open the brackets, we get 1 over 2a sec cubed theta plus sec cubed theta minus secant of theta. And this will give us 2 sec cubed theta 1 over 2a. Then we have 2 sec cubed theta minus secant of theta. But what was secant of theta? If you look back here from this expression, we could light that from that expression. See that from here, let me pick something. From here we can write secant of theta. If we make secant of theta the subject, we can write sec theta is equals to 2a times u. If we multiply both sides by a. So we want to replace secant of theta with 2a times u down here. So we get 1 over 2a. Then we have 2 times 2au cubed minus 2au. And this will give us 1 over. See that now we have 2 here in the first term and 2 in the second term. We can factor out that. And we get, when we factor out, it will cancel with the other 2. So we get 1 over a. Then we get 8 u cubed. There is a there. Actually we should have factored out 2a, because we see that we have 2a here and we also have 2a here. So when we factor out 2a, it will cancel with the other 2a. And then, because this is 2a cubed, so we will leave 2a squared times 2. Because this is 2 times 2. See that this quantity here is 2 times 2a cubed. 2 cubed also. So if we remove 2a from there, we would leave 2. Would leave 2. If we leave 2a there, then we will leave 2 cubed times a squared. This is what we leave in this part. Then this 2a comes out and cancels with the other 2a. So we'll get 2a cubed is 8. So we get 8a squared minus u. Sorry, there is a u here. U cubed minus u. This is the expression for the second derivative, d squared u by d theta squared. So in our expression, I want to write it somewhere up here in this page. In our expression, we had that fr is equals to mh squared u squared. Then we have d squared u by d theta squared plus u. This is the equation of motion. So we replace and write mh squared u squared. Then now, this we got 8a squared u cubed minus u. That's the second derivative, so we add u. And we get the result as, now you see this will give us 0, this 2. And we multiply out here, we get 8 a squared m h squared u raised to power 5. This is the law of force. This is the law of force for this particular case. 8a squared m h squared u raised to power 5 when we substitute. So basically, this is how we obtain the equation of motion for a particle moving in a central force field. So you can go through the other example. It is done. It is worked out exactly like the one we have done here. So go through that and you should be able to get it. You can get the notes on this in the Masomo platform. So those examples are there. Thank you for listening, and in the next video I'll prepare something on the projectile motion.